So welcome to Forensic Chemistry Lab. Before we get started talking about making solutions, let's go through the laboratory itself, and I'll point out a few features for you that will be useful throughout the semester. First, we have the acid cabinet under that bench on the left, and the base cabinet under the bench over there on the right. Here's a good tip for you. Ammonia is a weak base that we use a lot. People say ammonia, but they actually mean ammonium hydroxide. Ammonia is a toxic gas. We don't keep canisters of it around, but ammonium hydroxide is the solution version. So if you're looking to use ammonia, actually go get ammonium hydroxide out of the base cabinet. The next place that you really want to know in the lab is where the solvents are. You're going to use these a lot. They're in two different places. The first place is where we put the water miscible solvents. These are solvents that dissolve completely in water, mostly things like alcohols and acetone. Generally, these solvents are okay to use with plastic tubes and plastic pipetters and things like that. They're not going to introduce a ton of contamination or just dissolve the plastic, generally speaking. Methanol is in here, and methanol is our favorite. A good tip for you is when you're not sure what solvent to use, just try methanol and see if that works. It's usually a nice starting point. In the hood or under the hood, in the back left corner there, is where we keep the water immiscible solvents. These are things like chloroform and diethyl ether. And these can be really, really good solvents for extractions. They're water immiscible, meaning they form a second layer with water with aqueous solutions. And so this is going to be, we're usually going to use one of these and then an aqueous solution to do a liquid-liquid extraction. Now these are pretty non-polar, and they're generally not okay to use with plastic. Don't use these with plastic unless you are certain it's not going to be a problem, or unless you ask me specifically. That means don't use plastic containers. Don't use the pipettes with these solutions. That's a big one. We're going to use chloroform quite a bit, and it's not uncommon for students to forget and start pipetting chloroform with the plastic pipetters. That is not good for the pipetters. If you have to do something like that, talk to me and we'll figure out a plan. In the back right of the lab, that cabinet is where we keep the drug standards. You go there quite often. Please do not, as a courtesy to your colleagues, don't take them out and just leave them on your bench. Take them and use them and put them back. If you can't find something, the very first thing to do is to ask around the lab, does somebody have this out? Because that's really common. So take what you need and put it back. And please note that they are alphabetical in the cabinet. And let's try to keep that guy organized. It'll be better for everybody. If you're standing in the front of the lab and you walk over to the left, there you'll see the supply shelves that has containers and pipetters and a lot of common things that we use a lot, but you do not have in your drawers. When we're working with pipetters, it's okay to take a set of pipettes off of that shelf and put it down on the edge of a bench bay so that several people can access and you can share it. Keep the pipetters, you'll see there's labels there, keep the pipetters organized, and again, ensure that you don't just sort of keep them on your bench, because we've all got to use them, we've all got to share them, and we don't want that to be a pinch point. Now that we know where things in the lab are, let's talk about making solutions. So most instruments run solutions. Most instruments do not run solids or liquids. There are many exceptions, one of the most notable being FTIR, where you can directly run solids. But because most instruments run solutions, we're going to be making a lot of them. But most of the samples you get in forensic chemistry are solids. So you have to get pretty adept at going from solid to a known solution. So most drugs and explosives you're going to get are going to be solids. Ignitable liquids is a bit of an exception, but most of the time it's drugs, and those are going to be solids. And in our lab, your unknowns are oftentimes going to be solids, and you're going to go to the drug cabinet in the back, which are almost all solids. There's a few pure liquids, but they're almost all solids. So we have to get from solid to solution in a known, controlled way that makes sense for how we do business. A lot of the time in your previous chemistry and biology labs, you have been given a solution already. They say, here's a solution of such and such molar. And then sometimes you have to take that solution and you have to make dilutions from there, which is useful. But again, we're going to spend a lot of time going from solid to solution. When you did talk about going from solid to solution, you talked about using the most accurate proper tools, which is going to be a volumetric flask, which is a very wonderful, very accurate tool, but we use it pretty sparingly in forensic chemistry. And a big reason for this is cost. When you look at a lot of the teaching lab compounds that you've used previously, if we consider something like sodium chloride is about 0.8 cents per gram. And a lot of the drugs we use, and you'll see in forensic chemistry laboratories, on the cheaper end, like dextromethorphan, cost $20 a gram. And that's pretty typical of the prices that we pay in this class. So if you calculate, I would need a gram of solute to dissolve in 50 milliliter volumetric, that's not a big deal when you're talking about 0.8 cents per gram, but that's a pretty big deal when you're talking about $20 or $100 a gram. We'll usually I'll buy something like 5 grams of drug, and that'll last me oftentimes a couple years. So if you take, 20%, if you take a full gram of that to make your one solution or something, that is a pretty big deal. And you've significantly depleted the class's supply. So we really have to think about it. We use small amounts. So when you go out into the world and you're doing forensic chemistry and forensic toxicology, we use much, much smaller amounts than almost certainly any class, any lab that you've used up until this point. Out in the world, we use really small amounts of things. Also, we need really small volumes. The instruments that we run, when we run most of these solutions, they run 1 to 10 microliters of sample when you're running them. So if you made a 50 milliliter solution, that's 50,000 runs on the instrument, when usually you're only going to run that sample, 1 or 2, maybe 5, 6 times at the most. So it's a tremendous waste to make a big volume with a lot of mass of stuff. We need to deal on a much smaller scale. So before we get into the nuts and bolts of one way that you can make solutions on this much smaller scale, let's review what you already know about making solutions, and we'll base this on everyone's favorite concentration unit, molar. Okay, so we say molar or write capital M, and that's really a shortcut. It's a shortcut way of saying the true unit, which is moles per liter. Moles per liter, which we can write either of the ways that you've seen here, mole/liter or mole over liter, meaning moles of solute per liter of solution. Let's review a pretty straightforward concentration calculation. Let's suppose that you want to make 1 milliliter of a solution that is 0.5 molar. How many moles do you need to make that solution? All right, what I want you to do now is pause this video and do this calculation. Don't skip this part. Don't unpause it and be like, you know what, I'll look at it, I'll see it, and that'll jog my memory. This is a classic general chemistry trouble situation that we always try to point students towards. Watching someone else do it helps you very little. What really, really helps you is after you've seen someone do it, you do it yourself. So pause this video and do it yourself to show that you can do this. You've done it in other classes before, and if you're having trouble with this, you want to pause and you want to go back and review your previous classes. So pause this video and don't go forward until you have an answer. So this is a pretty straightforward calculation. There are other ways to do this, and if you learned some other way and you got to the same answer, that's totally fine. Lots of different ways to do it. I'm a cross multiplying guy. I don't think that's as popular these days, but I set it up as a cross multiplication and then solve for x. Let's look at another one. Suppose that you want to make a solution that is 0.5 molar. You have 0.007 moles of solute. What total volume do you need to make that solution from your 0.007 moles? Again, pause it here, calculate your answer, and then we'll go over it. Again, I set this up as a cross multiplication. There are definitely other ways to do it, and as long as you arrived at 0.014 liters or 14 milliliters, then that's great. So what we're saying here is if you have 0.007 moles or 7 millimoles of stuff, the final volume of that solution needs to be 14 milliliters to give you that 0.5 molar solution. Okay, last one. Let's do a dilution. Now that you have made a 1 milliliter of a 0.5 molar solution, you want to take that solution and dilute it to yield a 1 milliliter solution that is 0.025 molar in that solute. What volume of your stock solution, that 0.5 molar solution that you made, do you need to use to make this diluted solution? Again, pause here and get an answer, and we'll compare our answers. Okay, so we're going to use one of our best friends here, the dilution equation, M1V1 equals M2V2, and this is not appropriate for titration. Students try to use this for titrations. That's not what it's for, but it is wonderful. This is your go-to equation, simple ratio, when you're doing a dilution. So you set it up, M1V1 equals M2V2. It actually doesn't matter whether the concentrated and the dilute is on right or left. For my own sake, I usually keep the more concentrated solution on the right, and I keep the less concentrated solution on the left. What's really, really important about this, it's a ratio. You can use whatever units you want, but your units must be consistent. This will really mess you up in our lab. If you don't write your units and you switch them up, because we're going to go from milliliters to microliters a lot, that'll really mess you up. So in this case, you should have calculated I need 0.05 milliliters. Or when you go to use the pipetter, that's going to be 50 microliters. Alright, so before we go further in forensic science, we have to introduce a concentration unit that you probably have not run across yet. Molar is my favorite. I love moles, near and dear to my heart. Moles are wonderful. It's a wonderful way to explain the universe. But non-chemists don't tend to like moles, and they don't want to have to deal with them, and that takes molar down with them. So it's going to be very, very rare that you have to use a molecular weight for a molar conversion in this class, and really in forensic science. In forensic science, for the most part, they avoid moles, and that forces us to use a concentration unit that is not molar, and the most common unit you're going to run into is milligrams per milliliter, or sometimes we'll convert that to micrograms per milliliter or nanograms per milliliter. Alright, now try not to let that constant, it's one unit, milligrams per milliliter. We just say it like that. It's one unit. We don't think of it independently as milligrams and milliliters. It's one unit. And remember, though, molar is just made up. That capital M in saying molar, it's just a shortcut. The true unit is moles per liter. Everything we've been doing so far is moles per liter. So we're going to shift this new concentration unit, milligrams per milliliter or mig per mil. It just doesn't have a cool shortcut letter to it like molar does. So to illustrate this, let's look again at that calculation we just did, where we did the dilution calculation. All right, I'm not going to make any changes here. There's no substantial change here, but things are going to shift a little bit. So this is the exact same problem. This is the exact same solution that we just made. I just, instead of writing the shortcut capital M, I wrote moles per liter, which is the correct. That's what molar is. So I can say now that you have 1 milliliter of a 0.5 mole per liter solution, you want to make a dilution to yield 1 milliliter of a 0.025 mole per liter solution, Now I'm going to be very careful with my units. Notice I wrote moles per liter as a unit, and I wrote my units in there, and I kept it consistent when I did the dilution calculation. So we're going to take everything we just did with molar that you've done before and you're pretty comfortable with, and we're going to switch over to milligrams per milliliter. It's the same idea and everything. It's a concentration unit. It's very, very similar calculations that we just did. It's just that we've taken moles out of the equation. So let's revisit a very, 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 very similar version to that previous problem, but we're going to switch up the concentration unit. So suppose that you want to make 1 milliliter of a solution that is 0.5 mg per mil. How many milligrams do you need to make that solution? Again, pause now and try to work this out for yourself. So same math, if you didn't cross multiply like I did, you should be able to do the same technique and calculate that you need 0.5 milligrams. You need to add 0.5 milligrams to that 1 milliliter to give you a 0.5 mg per mil solution. So again, very similar math, very similar idea to what we did before. Suppose you want to make a solution that is 0.5 mg per mil. You have 0.007 grams, same thing as 7 milligrams of solute. What total volume do you need to make that solution? Pause and figure it out. Again, same idea as before. You need 14 milliliters. Now, when you start doing these calculations with solutions and at the scale we're making, you want to start to think in microliters. So this is 14,000 microliters. Okay, back to our dilution problem. So now that we have 1 milliliter of a 0.5 mg per ml solution, we want to make a dilution to yield 1 milliliter of a 0.025 mg per ml solution. What volume of our stock, that 0.5 mg per ml solution, should we use? So pause and figure it out. Same idea as before. We're going to do M1V1, M2V2, and again, mg per ml is a unit, and we can just use that unit here. Now I do have to backtrack a little bit and point out that these calculations aren't always going to work for you. You're going to run into real world problems. You're going to run into some kind of constraint that causes an issue. So here, if you calculated, I want to make 1 mg per ml, or I want to make a 1 milliliter solution of a 0.5 mg per ml solution, I'm going to go to the balance and weigh out 0.5 milligrams. You can't in any way accurately weigh out 0.5 milligrams on a balance. To try to do so is a pretty bad idea. In a similar vein, this calculation that we did, we ended up with 14 milliliters of solution, which it's not the end of the world, but that's a lot. That's pretty wasteful. If you're running around the lab making many milliliters of solution, you're generally wasting solvent, but more importantly, wasting drug. So you want to probably, when you do this calculation, you want to say, ooh, that's a lot of volume. I'm going to see if I can tweak something and reduce the volume on that. So let's talk about some solutions to these issues and one good way to make solutions. There's a lot of different ways to do it. When you go out in the world and you get trained, you might get trained a different way. That's totally fine. We also do have volumetrics that range from 1 to 4 milliliters, and you can use that. But this is a pretty good approach. But again, it's not the one true answer. There's tons of ways to do things, and you want to get real comfortable realizing that there's not some secret answer that I'm hiding from you. There are a lot of ways to do all of these different things we're going to talk about in lab. But let's look at one example that's probably my favorite way to make solutions for forensic chemistry. So head to the balance with a container of choice. Tear that container, make sure you have something to write on, and you can take the container out of the balance at this point. You can also do it very carefully on the balance, as this adept student is doing, but please be careful if you're going to do it on the balance. And she has a pretty good eye here. She's going to add a small amount of this ibuprofen into that container. She got it all into the container. If you get any outside of the container, you need to clean up the mess. She's going to close the door, wait for the little circle to disappear, and record 0.0091 grams. Think about how many milligrams that is. It's really important. You don't want to confuse this point. That is 9.1 milligrams. So she went to the balance and she weighed out some amount, some known amount, and that's fine. That's great. And she wrote it down. She did not sit there all day long trying to hit some predetermined mass that she had in her head. She didn't sit there trying to go flake by flake and hit 5.0 milligrams. Do not do that. It's a tremendous waste of time and effort. And if you're afraid of the calculations, you really got to learn them. You're going to get really good at them. You're going to do it over and over. So it's better to do it sooner rather than later. Do not waste your life at the balance trying to get some exact number. Just go there, weigh out some amount, and write down that you know you have that specific amount. Another tip I would give you is, in that earlier calculation, we got 0.5 milligrams. And you might say, well, the balance reads 0.5 milligrams. Why don't I just go to the balance and try to do 0.5 milligrams? It is very, very difficult to handle sub-milligram or low milligram quantities and to get an accurate read in the balance, but more importantly, to handle that small amount and not lose things. That is to say, the accuracy of the concentration of the solution that you're going to make plummets when you go, in my opinion, below 5 milligrams. So I generally, if I want, and it depends on what you're doing. A lot of times you just need a ballpark concentration. It doesn't really matter. But for this first making solutions lab, you'll be graded on the concentration. And I definitely would not go below 5 milligrams. So if you do some pre-calculation and decide, I need 1.0 milligrams, don't sit at the balance all day trying to hit precisely 1.0 milligrams, and don't even mess around at that low mass. it's going to be trouble. In the next step, we're going to go ahead and decide what concentration we want to make, and then do the calculations and figure out what volume to add to make it. So we do the calculations. A good way to do it is do the calculations after you have a known mass. And you're going to ask yourself, what concentration should I make? The answer is whatever you want. It's flexible. That's oftentimes very confusing for students. But the most common solution that you'll see in forensic chemistry, when you order standards, they tend to be this, is a mg per mil. A mg per mil is a really common concentration. A lot of instruments read things well at a mg per mil. And you can dilute from there pretty easily. Most things are soluble at that concentration, so it's a really common concentration. It is not the only concentration by far. And then when in doubt, methanol. So the most common solutions are going to be mg per mil solutions in methanol. So if you're unsure yourself, just try that first, see if that works for you. Okay, so now we are going to go back and do the calculations and figure out what we want to do. So let's suppose that we do want a 1 mg per mil solution. Well, then we can say to ourselves, all right, I want a 1 mg per mil solution. I have 9.1 milligrams. Well, that means I should add 9.1 milliliters or 9,100 microliters of solvent. And I can go over and get the 5 mil pipetters and add that pretty much that precise amount of solvent. Okay, so we're going to go over to some reservoir of methanol that we want to be very, very clean, and pipette our volume that we calculated into there. Now, very, very importantly, we are going to check to make sure that everything has dissolved. If everything hasn't dissolved, you can't get it to go in. If there are particles in the bottom, then that solution is not good. You got to dump it and try something else. Sometimes it'll dissolve if you leave it overnight. It just takes a while to go in the solvent. But if you have particles in the bottom, if you shake it up and you look up at the light and you can see particles, you can just see undissolved things, then you cannot know what the concentration of that is without very, very significant effort. So you pretty much have to start from scratch. So you have to make sure that it's dissolved each time you make a solution. Now, in truth, I kind of fibbed to you here. In fact, she did not add that 9.1 milliliters of solution. She added 3.03 milliliters of solution to make a 3 mg per mil stock solution. Now, why would you do this, you might ask? Well, in this case, it was just her being nice so we could illustrate a point, but this is one of those ways, this is the biggest way to overcome those real-world constraints. One is that container that she has doesn't hold 9 milliliters. So if she tried to pipette 9 milliliters in there, it would overflow. But you don't have to quit and start again and say, oh no, it doesn't hold 9. My calculations say I need 9. Just change your concentration. You can make whatever concentration that you want. So this is a really common way to get around some of those real world problems, is just change your concentration. Usually make a concentration that's a little bit more concentrated and then dilute from there. So let's consider this in the context of some of those calculations we did before. We ran into real-world problems. When we wanted to make our 0.5 mg per mil solution, and we said, oh, we need 0.5 milligrams. Oh no, what are we going to do? We can't weigh that in the balance. Well, just make a more concentrated solution and then dilute that solution down to 0.5 milligrams per milliliter. One of the other problems we ran into in those example problems was I said, ooh, I need to add 14 milliliters. I don't want to add that. That's kind of a wasteful solution. That's a lot of solution. I don't want to make the one that big. Well, if I had gone over to the balance and I had weighed out that mass of stuff, I can just add less volume and calculate for a more concentrated solution and then dilute down from there. One caveat here is that you do have to watch out for solubility. You can't just make everything at 50 milligrams per milliliter. Something will dissolve at that, but most drugs aren't going to do well at that. A good guideline is a mg per mil. Almost all drugs will dissolve at methanol at a mg per mil, but you probably will run into a drug this semester, or at least a few of you, that doesn't dissolve well even at a mg per mil in methanol. So you have to keep solubility in mind, but a rough guideline here is going to be a lot of things are going to dissolve at 5 mg per mil or less. If you're going above that, you can always just try it. And then if it doesn't dissolve, then try something else. There's going to be a lot of that in this class. Try something, see how it works. And if that doesn't work, try something else. So we said that in truth, she made a 3 mg per mil solution. And now she has to go ahead and dilute that down to the desired 1 mg per mil solution. So she's going to do her M1V1, M2V2 calculation here. and plug in her 3 meg per mil stock, and the X is how much of that do I need to add to my final 1 mil solution, or to my final total volume 1 mil solution, to get a 1 meg per mil concentration. And her answer is 0.33 milliliters or 330 microliters. So to actually perform this dilution, she is going to withdraw 330 microliters of that 3 meg per mil stock solution and deposit that into an empty container. She really only needs a container that holds a milliliter because she knows it's going to be a milliliter. And then she is going to dial the pipette to 670 milliliters because it has to be, 670 microliters. It has to be 1 milliliter total. So 670 microliters of this methanol that she's adding, plus the 330 microliters that's already in there, is 1,000 microliters total, or 1 milliliter. And now she has a wonderful known 1 mg per ml solution in methanol of ibuprofen.